Welcome students. In today's lecture, we are going to solve our next quantum mechanical problem, which is particle with a potential step, making use of Schrodinger equation. Let us first see what this problem is. This is problem of one-dimensional potential step. This word step you probably can visualize with moving a level up or down. For example, while walking on a smooth flat surface, if you need to go at some higher or lower level, then you need to use steps to move up or to move down. In the similar manner, try to capture the situation of potential step. Here, while moving in a region of low potential, say 0 here, suddenly you face ahead a high potential region so that the situation is called now a potential step at this position x equal to 0. This means that in order to move ahead in next region, we have to step into a high potential region where the potential here in this figure is V naught. So this problem of potential step belongs to a force field that is imposed on a particle which is zero everywhere except for a certain region, and in this figure this region starts from x equal to 0 position in the positive x direction. Mathematically, this situation can be written as Vx, the potential, which is 0 for x less than equal to 0, and this potential Vx is V naught for all the positions which are greater than equal to 0 right from the figure. Now the height of this potential step will be here the V naught. Now turn to the solution. For the solution of this problem, we will make use of Schrodinger wave equation. This we have written as region A and this is region B. Region B is a finite potential region where the potential is finite equal to V naught. Now the particle is moving one dimensional in the positive x direction. Here starting from region A, let us say the particle is moving towards region B. In the region A, the particle is totally free. रीजन ए में पार्टिकल पूरी तरह से फ्री है क्योंकि वो जीरो पोटेंशियल रीजन में है. जीरो पोटेंशियल का मतलब उसकी पूरी एनर्जी जो है वो सिर्फ काइनेटिक एनर्जी है. द पोटेंशियल एनर्जी पार्ट इज जीरो. सो बाय द टाइम इट अप्रोचेस x equal to 0 point, it is facing ahead a potential hill, a hike in potential. And this high potential interrupts its free motion. इस हाई पोटेंशियल की वजह से, इस हाई पोटेंशियल हिल की वजह से उसका मोशन है वो इंटरप्ट हो जाता है. इट जस्ट गेट स्लो डाउन. नाउ हाउ this situation can be solved, how this motion of this particle can be solved and described. We will write Schrodinger equation for the motion of the particle and then we'll try to solve that. Next, we will try to discuss the obtained result both in the classical viewpoint and the quantum viewpoint. So students, we see two situations here. The first situation is that the particle in the region A has sufficient energy to cross the potential hill, just like the vehicle which has enough speed and easily crossed the road bump. The second situation is that the particle doesn't possess the sufficient amount of energy which is required to cross the potential step. Just like here, the old man who is unable to cross over the road barrier and is back into the region A. So let us first discuss the case when the energy of the incident particle is greater than the potential step V naught. And we'll begin with the classical viewpoint, which says that a particle is a particle. It means that when a particle hits on a potential wall and has the energy E greater than this potential V naught, it will simply get into the region B, just like the vehicle which very easily crossed the speed breaker. You see, on approaching x equal to 0, the particle will simply get slowed down as it experiences a retarding force due to this potential step. But it will still continue its motion and enter into the region B. The reason is the energy is greater than V naught. The energy E possessed by the particle is greater than the potential wall V naught. And using the classical mechanics results, we can also write momentum in both the region as momentum equal to 2me under the root, and in the region B where the particle has energy E minus V naught because a certain amount of energy has been spent during crossing of the potential step. So here the momentum in the region B becomes 2m into E minus V naught under the square root. Next we see the quantum viewpoint, which says that according to de Broglie hypothesis, every particle is associated with a wave nature. And it implies that when a wave hits onto a potential wall, then along with the transmission probability, it has also certain probability of getting reflected back. And the motion of the wave in quantum mechanics is always governed by the Schrodinger wave equations. And for the solution of this situation, this problem, we have to solve the Schrodinger wave equation in both the regions A and B. You see, here the potential Vx is equal to V naught, which is independent of time. So we will make use of time independent Schrodinger wave equation to observe the particle motion. This is the Schrodinger wave equation which we had derived in the previous lectures, and now we have to find out its solution. So this is the equation for which we have to find out the solution in both the regions, region A and region B. So let us first solve it in the region A, where x is less than 0 and the potential is 0. So after putting v equal to 0 in this equation takes the form curly square psi 1 over curly x square plus 2m over h cross square into e psi 1 equal to 0. Now this term in this equation can be written in the term of wave propagation vector, and in using this I have made use of relation as e equal to p square by 2m, from where p can be written as 2me under the root. Also, p can be written in terms of wave propagation vector as product of h cut and k. From here, I could write k equal to 2me square root over h cross. And now the equation becomes this, for which I have to find out the solution. In mathematics, the simple solution of this equation can be written in terms of exponentials. So psi1, the solution of this equation, can be written as sum of these two terms. The first term of this equation explains the incident wave in the region A, while the second term in this equation explains the reflected wave in the region A. You can also see it from the argument of exponential. You see, the positive argument describes that the wave is moving towards positive x direction. So it must be the incident wave part. In the second term, the exponential has negative argument, which says that this part is for the wave which is moving in the negative x direction. So it must be the reflected wave. Similarly, we solve this equation for the region B. In the region B, x is greater than 0 and the value of potential becomes V naught. So just replace V by V naught in this equation and again write it in terms of wave propagation vector by making use of the same relations as in the region A. I could write the Schrodinger equation in this form. Again, the general solution of this equation can be written in terms of exponentials, and the first term in this exponential can be again explained by checking the argument of exponential. Here, the positive argument explains that the wave part is moving in the positive x direction, which must be the transmitted wave, which must be the transmitted wave as it is moving in the positive x direction. Now, this negative argument of exponential explains the reflected wave in the region B. But you see, students, there is no any reflected wave. Moreover, there is there is no any source of particle generates particle that can move in the negative x direction, nor it has any other potential step which can reflect the transmitted wave back into the negative x direction. So I simply take d equal to 0 here and this terms cancel out. And the solution of psi2 can be written in terms of first term only. So now we have calculated both wave functions in region A and B, and these are the solutions, but still we have constants A, B, and C unknown to us. And to evaluate these constants, I will make use of boundary conditions. What does boundary condition say? It says that the wave function must be continuous. Since there is a discontinuity at x equal to 0 for the potential, the wave function in the region A, which is psi1, and the wave function which is in the region B, psi2, must be equal at x equal to 0. At x equal to 0. So I just substitute the values and put x equal to 0. And from here, I arrive at this result of arbitrary constants, which is a plus b is equal to c. I label this equation as equation 3. Next, just like the wave function, its derivative also must be continuous at x equal to 0 despite of discontinuity of the potential. So I take the derivatives of equation 1 and 2 and equate them at point x equal to 0. These are the derivatives. Put the values of x equal to 0 and you just arrive at a minus b equal to k2 over k1 into c. This equation is equation 4. Now we can solve equation 3 and 4 to evaluate the values of a, b and c. If I add both these equations, I can get the value of c in terms of a. And if I subtract equation 4 from equation 3, I can get the value of constant b, that too in terms of the constant a. So you can substitute the values of b and c back into the equation 1 and 2 in order to get the complete wave function psi 1 and psi 2. So these are the wave functions with incident part, reflected part, and in region B there is only transmitted part. And if I individually write them, then I can calculate them. This is incident part, this is reflected part. I have substituted the value of B and the transmitted wave part after substituting the value of C. I can also write the complete wave functions in the region A and region B, and both these equations explains the solution of the Schrodinger wave equation. Now you see, as classical mechanics says that when a wave hits a potential step, then along with transmission, there occurs reflection also. So in order to validate this point, I calculate the reflection coefficient and the transmission coefficient. By definition, reflection coefficient can be written as the reflected probability density current divided by the total, I mean the incident, which is the total probability density current. And the reflected probability density current can be written as the product of velocity in the region A and the probability psi star. Psi is the wave function and psi star its complex conjugate, which gives us the probability density, and its product with velocity gives us the reflected probability density current. And similarly we can write it for the incident wave part, and the reflection coefficient can be calculated on substituting the corresponding values of wave functions, as VA from here get cancels out, and we are left with this part which represents the reflection coefficient. Next, you calculate the transmission coefficient using the similar definition, and after substituting for the wave function, the transmitted wave part, you can get the value of transmission coefficient. Now the major point to observe here, to notice here, is that the reflection coefficient is a non-zero quantity. It means that there is definitely certain probability of the wave to get reflected back. इसका मतलब यह है कि R जीरो नहीं है. इसका मतलब कुछ वेव पार्ट इंसिडेंट का डेफिनेटली रिफ्लेक्शन बियर करता है, जबकि क्लासिकली हमें ऐसा कुछ देखने को नहीं मिलता. क्लासिकल मैकेनिक्स सिंपली सेड दैट if the energy of the particle is greater than the potential step, it will, in a complete manner, transmit into the region B. Now, this result R non-zero is contrary to the classical mechanics predictions. Next, transmission coefficient, which is also certain quantity but is not equal to 1. Classical mechanics also explains that the particle will get fully transmitted into region B. So according to classical mechanics, it must be unity. The value of T must be unity. But as it is not equal to 1, it means that there is not full probability of transmission, just because certain chances of reflection also occurs here. This is again contrary to the classical predictions. So whatever we have solved till now is the case where the total energy of the particle was greater than the potential step. The particle has simply the chances of transmission into the region B. Now, think of the second case where the particle does not possess sufficient amount of energy and has the chances of being only in the first region. And to discuss this and to solve this case, let us join in the next lecture. Thank you, students.